Hi everyone. This is the video lecture for the Chapter 4 lecture slides on work and energy. So we talked about force and motion already. A force is what causes motion. Now we're going to stick with the idea of forces and carry that a little bit farther and talk about how that relates to energy. So starting off with work, work is just force times distance. So we're not going to start off with we're going to jump right into this with an equation. And I want to point out here one quick thing, that this is parallel distance. So what that means is that if I apply my force and my object moves in the same direction, those are completely parallel. Now, but it's possible though that maybe I'm pushing up and to the right and my object still just moves to the right. Maybe it's constrained somehow. Or like on a lawnmower, if I'm pushing down on the handle, pushing down at an angle, the lawnmower is still only going horizontally. So force and the distance that the object moves don't necessarily have to be the same direction. So what counts is this parallel distance. So I would pick out whatever, so if I'm pushing down, like on my lawnmower, and it's going that way, I would pick out whatever component of my force is in the direction of motion. And that's what I mean by parallel distance. One thing that's nice about work and energy is that those are not vectors, so we don't have to worry about any kind of direction or anything. And the units for energy are called joules, so it's a derived unit, and it's special enough to get its own name. So a Newton times a meter, that's a joule. So quick, just to talk a little bit more about parallel distance. In this example, someone is pushing against a wall. They're exerting a force. They're not moving anything. So the distance is 0. So there's no work done. Even though you might feel like you would be exerting yourself if you pushed against a wall all day, your muscles are doing work, but you're not doing work on the wall. We'll talk more about that distinction coming up. Here, this person is applying a force and the object actually moves. In this case, technically, they've done some work. And in this final example, this person is mowing their lawn. So they're pushing, their force is exerted along the handle, so down and to the right. And since force is a vector, that means it's got some piece going to the right and some piece going down. Only this right going piece of the force contributes to work. The part that you're pushing down with, we don't consider that for the purposes of calculating work. All right, question number 2. Work is done on an object when it is moved, stationary, acted on by a balanced force, all of the above, or none of the above. Again, all of these answers at the very end with some explanations. Now, whenever we're doing work, usually we feel some force acting against us, and that's usually a Newton's third law type of situation. For every force, there's an equal and opposite force. If it's gravity, if that's the force we're trying to overcome, like if I'm trying to lift up my stapler, I've got to overcome the force of gravity pulling this down, then my unbalanced force to cause this to move up has to be greater than the force of gravity pulling it down. So the way that this ties into energy is that any object or system that has energy has the ability to do work. Energy and work are very, very similar things. So similar that they have the exact same units. So whether or not something does work or has work done on it is going to relate to whether it gains or loses energy. So when something does work, so when a system does work, it loses energy. That's what I mean when this says work is done by a system. That system is losing energy. The reverse of that, if work is done on the system, that means that system is gaining energy. So if we think about it this way, a better definition of work is really more along the lines of it's a process of transferring energy from one object to another. Now, when we talk about energy, it's going to come in different forms. The two main forms that we can break energy down into are kinetic energy and potential energy. So kinetic energy is energy something has because it's moving. And almost everything has kinetic energy. Even something at rest has a little bit of kinetic energy because the atoms and molecules that make it up are moving really rapidly. So anything that's not at absolute zero has some, at least, atomic or molecular kinetic energy. Now we have an equation for kinetic energy. It's 1/2 mass times velocity squared. So one equation is 1/2 mv squared. So that's one equation for this chapter. What are the units for kinetic energy? It's energy, so its units are joules. All energy has the same units. Quick example of where this might be practical. If we have to stop our car really quickly, because this speed or velocity shows up squared in the kinetic energy, if I double my speed, it actually takes 4 times the distance to stop. If I triple my speed, my braking distance goes up to 9. That's why you've got to slow down when you go through a school zone, is because how long it takes you to stop is really sensitive to how fast you're going. Here's some data that I got from Department of Transportation, stopping distance versus speed. So this green line that's going horizontally, that's roughly 1 city block. If you hit that going 60 miles per hour, it takes you the entire block to come to a rest. Right, question 3. This one's a little bit complicated, but you guys can do it. A truck has twice the mass of a car, and both are going at the same speed. If capital K is the kinetic energy of the truck, what's the kinetic energy of the car? Okay, the other kind of flip side of the coin of kinetic energy is potential energy, and that's the energy some object has due to its position. And there's a lot of different ways position can factor into this, kind of a real general idea. So if I lift something and put it high up on the shelf, that position is how high it is off the ground. If I compress or stretch out a spring, the position is how much it is stretched out. A magnet attracting a paper clip, the closer the two get to each other, the bigger the force is. So there's bigger energy. And even the protons that make up the inside of an atomic nucleus have some potential energy. That's where we get nuclear power from. The potential energy that I want to focus on for this chapter is gravitational potential energy. So the energy something has that lift it up, maybe put it up on the shelf or something. That is energy that an object gets from us working against gravity to lift it up. So whenever we lift something up, we are working against its weight. So this gravitational potential energy is weight times height. What we're doing here is force times distance. And we already know what the force is when we're talking about weight. It's mass times gravity. And if we think about our distance as being height, then our weight times height ends up being mass times gravity times height. So that's our equation for gravitational potential energy. And since it's energy, its units are joules. One interesting thing about gravitational potential energy, whenever we're giving something gravitational potential energy by lifting it up, it doesn't care how we lifted it up, just the difference between the start and the end point. So in this cartoon here, if I slid this object up a ramp versus lifting it straight up, in both cases, it's changed the same potential energy. We can also choose where we want our reference point or our 0 point to be. Usually, we take our gravitational potential energy to be 0 on the ground. So going up off the ground is positive potential energy. But if you dug a hole, in that case, if it fell into the hole, it would have a negative potential energy. If you didn't want to do any negative potential energies at all, some people don't, you could make your reference point 0, not at the surface level, but you could drop it to the bottom of the hole. That's what I mean by saying the reference point for measuring height is arbitrary. Okay, so we're about to get to the most important part about energy. It's the capacity for doing work. It can be transformed from one kind to another. Like gravitational potential energy can get converted to kinetic, back and forth. We cannot create or destroy energy, though. So energy has to be conserved. That is the one law that goes through all physical science. That works for biology, chemistry, physics, atmospheric science, whatever. That's like the basic law. So if I have a system that's completely isolated, its total energy remains constant. That's another way of saying energy cannot be created or destroyed. But you can make it change form. And this happens all the time, going from kinetic to gravitational, or from some other form of potential energy to kinetic energy, all the time. So a couple different forms of energy that are useful for humans and society. Thermal energy, so heat energy. That's kinetic energy, but on a molecular scale. Electrical energy is the energy associated with moving charges, and that's going to involve another fundamental quantity, charge. Chemical energy, like when you burn something to create heat from a fire, that's energy that we're getting from molecular bonds, so how atoms are positioned relative to each other. And nuclear energy comes from breaking apart or putting together bonds on a subatomic scale. All of these forms of energy are used in modern technology. Right. So some of these things on chemical energy and energy forms coming up, I'm going to go through kind of quickly in the video because there are things that you guys can, they're not hard to get. One of the interesting forms of fossil fuels down here is methane hydrate. And that's a weird case where you have natural gas like methane that's trapped in ice, and that ice is essentially underground. So you can one kind of more modern way to extract methane is by drilling into these methane hydrate, essentially ice fields, and extracting methane that way. So on the left, that's a picture of methane hydrate. It is essentially ice, but it's got methane trapped in it, and it will actually burn. To me, that's pretty cool. A couple slides on how much fossil fuels we use in the U.S. Oklahoma, we use about 31% more energy per person than the national average. These different kinds of alternative and renewable energy are, they're going to be important coming up to, in my opinion, moving forward as a civilization. So just a couple quick notes on these alternative or renewable forms of energy. Usually, if it's alternative, it's renewable. Those usually go hand in hand. Can't think of any off the top of my head that are non-renewable and alternative. Hydropower is interesting. There is a significant amount of change to the landscape when you do that. There's a loss of agricultural land. A lot of these good dam sites have already been taken up and converted into dams. And when you do that, when you block up a river and fill everything up behind it, there is significant environmental and ecological damage. And when they were building a lot of dams in the 30s and 40s, there was a significant amount of cultural damage, where the Glen Canyon Dam is a great example, where there were river going through. You couldn't not find native artifacts. It was just literally littered with pots and all sorts of really interesting stuff, and they just filled that up behind it. You should definitely look up the Glen Canyon Dam and these Anasazi artifacts. There's a very incredible documentary about 3 people that went through there right before they filled that up, and just the stuff that they were finding. Wind power. We've been using wind power for a long time, not necessarily for electricity, but to grind grains or to pump water. So in a sense, it's old technology. Using it to make electricity is relatively new. You have to have conditions where you have not just really, really fast wind, but it's more important that you have consistent, constant wind. So you want to be generating roughly the same amount of energy all day and all night. There's definitely some environmental effects. Bird and bat mortality goes up. If you've ever seen some of these large wind farms, the blades are incredibly long, and a lot of them are very hard to, like, when the windmill is done, what do you do with these long blades? A lot of them are just thrown away. But it's still a very promising source of electrical energy. There's a company in France that's working on these really cool new blades for wind farms that are recyclable. It's real awesome. Solar power is another good example of a future source of reliable and hopefully economic energy. It's definitely in use now, and you can use solar power in a lot of different ways. kind of like wind power, we've been using it for a long time, maybe not the way you think. So using the sun to heat up water is relatively, it's very old technology. You can also use solar power to generate electricity directly, which is what solar cells do. So in a house that collects light and directly converts it to electrical energy. You can also generate electricity from solar energy thermally. So that's what solar thermal electricity is. So this works kind of like a coal-fired power plant in the sense that you're using generating heat energy to create steam, to turn a turbine, to generate electricity. This doesn't use coal to do that, obviously. It uses solar thermal energy from the sun. Geothermal energy is another really interesting alternative and renewable energy source. This is very site specific, though. You need to have access to a large natural change in ground temperature between what's accessible at the top and not too deep down below. Really easy to see if you've been to Hot Springs, Arkansas. Little rivers flowing through town are almost too hot to touch because that's hot water relatively close to the surface. I think Iceland uses, that country uses geothermal energy for close to 80% of all their energy use, even electricity. And the last one I want to talk about is tidal power, and that's using the tides moving in and out throughout the day to generate electricity, very much like how you'd use a windmill. And the picture is going to look like a giant windmill that goes underwater. Now in France, they've been using tidal power to generate electricity since the 1960s. So cartoon picture on the left. So two giant propellers in the water. These fish are terribly wrong sized because you can see on the right, here's an actual picture, and these blades are huge. There's a tiny person, or the person down here appears tiny. The blades looks like there's one facing each direction because this is a bi-directional handle currents going in and out. Which to me it's a pretty neat idea. Last thing I want to talk about are biofuels. So that's using something other than a fossil fuel to burn to generate electricity. One way is by using plants to make ethanol and burning that. Drawback to ethanol production is that a lot of times it takes more energy to grow and process plants into ethanol than you actually get out. But another kind of side to this is biomass. And biomass is really anything that you can grow and burn, that's fuel. So any organic material, hold on one second. Okay, I have to make a quick distinction here when I'm talking about organic matter. Organic in this sense means something that was alive and then died, not organic like you would get at Whole Foods or something. So if something was alive and it's alive and lives and dies on a renewable basis, so it's not renewable, or it's renewable unlike coal or something that's already been kind of processed. A lot of biomass can come from interesting sources, like stuff from agricultural crops that's not used, wood scraps, animal waste, municipal waste, aquatic plants. What's municipal waste? It's a really nice way of saying human waste. If you can burn it, you can use that to generate energy. And one of the pros to biomass is that it's considered to be CO2 neutral, in that when the thing grew and lived, it consumed carbon dioxide as part of that life cycle. So when you burn it, you're releasing back into the atmosphere carbon dioxide that it had already taken out. And in that sense, it's not releasing any extra carbon dioxide into the atmosphere, which fossil fuels do. So that is, you burn coal or oil, releasing carbon that's been kind of hidden away down in the earth for millions and millions of years, and that's kind of adding more to what we already have. When a plant grows, it sucks carbon dioxide out of the atmosphere to live. When you burn that, you're releasing some of that back in, but that's technically CO2 neutral. And that's a benefit. The University of Iowa gets 12% of their energy from burning oat hulls. So part of the oat that's not used to make your oatmeal. And they estimate that they've been able to take the equivalent of 1,200 cars off the road by reducing that amount of CO2 through these oat hulls. Not too far from where the University of Iowa is, in Iowa City, so up in Cedar Rapids, there's a Quaker Oats factory. If you've been up there, Cedar Rapids is the city of 5 smells. And one of those smells is the cereal factory. Okay, don't mean to end on that kind of weird note about the cereal and the city of 5 smells, but here we are. The next couple of slides are the explanations to the questions that were available throughout these lecture slides.